Hi, hello, welcome back to our channel, our beloved channel Chemistry with RK. So today I have come up with our continuous topic on the previous lecture, that is, we were talking about alkanes, right? So in the previous video I have given the introduction for the alkanes. In this video I am going to discuss few of the preparation methods of alkanes. Actually we have so many preparation methods of alkanes, but among them I have chosen these three reactions which are very important. Again, when it comes in terms of objective, these three particular reactions have a huge weightage actually. Sabatius-Sunderens reaction, Wilkinson catalyst, that is trisphenyl phosphine rhodium 1 chloride. Yes, we are going to see what is Wilkinson catalyst and how does it works in the preparation of alkanes and all. And then the third one is coal base electrolysis, very important. When it comes to the priority, when it comes to the importance of these particular reactions, yes, we have huge importance in the organic chemistry, especially when it comes to IIT mains and advanced, and when it comes to medical side it is NEET. Yes, these reactions are going to play major role in this particular preparations of alkanes. Before we start the video, I would like to request, if you are new to the channel, please do subscribe and then don't forget to click on the bell icon to get the regular updates. Yes, I have been showering with a lot of love. I have been getting a lot of support from your side. Please, I request you to spread the same kind of love throughout our journey. So yes, without any late, let us just move into our lecture, that is preparation methods of alkanes. Particularly, I am going to discuss Sabatius-Sunderens reaction and then Wilkinson's reaction and then coal base electrolysis in this particular video. Yes, I am going to go into from minimum basic, like what and all you have to know. Firstly, to define normal reaction. What is a normal Sabatius-Sunderens reaction? But from that point, I am going to take you to the advanced level. Yes, I have selected a lot of questions from past 5 to 10 years papers on this particular concepts. So parallelly, I am going to solve those questions after discussing our particular concept related to these particular reactions. Okay, yes, without any delay, let us go into the video. Please, I request you to write down, to separate the information I am going to give you in this particular video. That will help you. Yes, I have been getting so many comments personally since I have given my WhatsApp number. So I have been getting continuous replies, continuous comments. That is, your notes is helping a lot in solving previous JEE question, previous NEET questions. So please, I request, a lot of students are taking my words so hard, so that they are trying to solve questions from previous NEET and mains papers. So they are getting a lot of happiness through the notes and then through the information they get from these videos. Okay, right? Please try to figure out, try to separate the information I am going to give so that it will help you to solve the previous JEE questions. Okay. Yeah, without any delay, let us start the today's video, that is preparation methods of alkanes. So we are going to prepare alkanes from various compounds or various organic compounds. Okay. So we are going to see preparation of alkanes from alkyl halides, preparation of alkanes from alkenes, from alkynes, and even carboxylic acids, even aldehydes, ketones. Most of the functional groups में से हमको alkane preparations अभी हमको देखने के लिए मिलेंगे. Right? You please let us start with the first one, that is hydrogenation of unsaturated hydrocarbons. So this particular reaction is also called as Sabatius-Sunderens reaction. So hydrogenation of unsaturated hydrocarbons and Sabatius-Sunderens reaction are both same. Okay. So what we are going to do is, we are going to take unsaturated hydrocarbons, which includes alkenes and alkynes. So now what do you mean by, first of all, hydrocarbons? See, the meaning of hydrocarbons is a compound which contains only hydrogen and carbon are called as hydrocarbons. Okay, so in that particular compound you will see only hydrogen and carbon. Other than hydrogen and carbon, if you have any other oxygen, nitrogen, then we can't call it as a hydrocarbon. Okay, especially when it comes to hydrocarbon, alkanes, alkenes and alkynes comes under this category, right? Yes, hydrocarbons. And now, what do you mean by unsaturated? The meaning of unsaturated is the compounds which contains at least carbon-carbon multiple bonds in between them. So generally alkenes में carbon carbon के बीच में double bonds दिखने के मिलेगा, and then even we can have carbon carbon triple bonds in the alkynes. So hence we can call them as unsaturated. And now when it comes to alkanes में carbon carbon के बीच में you will see all single bonds which are nothing but sigma bonds only. So we can call it as saturated hydrocarbon. So among the three, that is alkanes, alkenes and alkynes. Alkanes are the saturated hydrocarbons. This particular thing, I have explained in my previous introduction video of alkanes. So please go back, if you didn't watch that particular video, please go back to that video and then watch about the introduction part, because I am going to use those concepts in the coming preparation methods and then chemical properties of these alkanes also, not only in alkanes, in the coming organic video lectures. Okay, so please watch that video also. Okay, let us continue. And now I hope you understood what are hydrocarbons, what do you mean by unsaturated. And the next one is hydrogenation. Yes, generally in organic chemistry we have so many terms which are very important to discuss. So let me give you hydrogenation. Yes, if we talk about hydrogenation, yes, we are going to see these terms very frequently in the coming lectures. That is, hydrogenation is addition, okay, addition of H2. Yes, H2 molecule हमको add करना है. Yeah, next opposite to hydrogenation is dehydrogenation. Yes, so whenever you get the term or get the word D, which means that we are going to remove, okay, so that is removal of hydrogen. That is, we are supposed to remove hydrogen from the existing molecule. Okay, similarly let us go for hydration. Yes, what do you mean by this hydration? So it is said to be addition of H2O, that is water. If we try to add water, then we are going to call it as hydration. And then what do you mean by dehydration? Yes, this is quite opposite to hydration. Dehydration, that is removal of water. Okay, right. Halogenation. Okay, halogenation. And then which is nothing but addition of halogens. Okay, addition of halogens. Generally we define or we denote halogens as X2, where X is the 7th A group element. Okay, and then next dehalogenation. Yes, so this is nothing but removal of halogens. Okay, yeah, next hydrohalogenation. Yes, if we just try to understand about hydrohalogenation, then it is said to be addition of HX, that is hydrohalogen. Okay, hydrohalogenation. And then next, this is quite opposite to dehydrohalogenation. Which is going to be the removal of, yes, we are supposed to remove hydrohalogen. This particular reactions we are going to see more in the alkenes in the coming next topic. Okay, right. And then we have halohydration, that is halohydration. Okay, halohydration. Yes, what do you mean by halohydration? That is addition of HOX, that is when we react halogen with water. Okay, so halogen, that is H2O, and then if we try to react with halogen, then we get HX plus HOX. This is said to be halohydration, that is hypohalogenation we call particularly, that we'll see in the coming videos. Okay, and then next one is carboxylation. Okay, carboxylation. Yes, this is actually called as addition of CO2, carbon dioxide. Okay, right. And then next, if we move on to this decarboxylation. Yes, what do you mean by this? This is opposite to carboxylation. It is nothing but removal of CO2. Right. So these are the terms which are very important to understand the organic chemistry, especially when it comes to reactions part. Yes, we need to know about these terms so that it will be helpful to us in understanding very easily. Okay. And now let us see what happens exactly during addition reactions. Okay. So generally when we are trying to add something onto the multiple bonded system like alkenes and alkynes, generally we see that there will be a breaking of one pi bond, and then in place of that one pi bond we are going to see two new sigma bonds. So let me just take the example here, that is, generally we know that alkenes will have, carbon-carbon double bond particularly. When we react this with hydrogen that is H2, then what we are going to get here is carbon will have the remaining bonds, but whereas when it comes to the pi bond in between the carbon is going to go out, and then in place of that one pi bond we are going to see two new sigma bonds, which is nothing but the two hydrogens will be added onto this carbon. Yes, please try to understand, try to observe the valency of this carbon. Yes, it is going to be 4 here, and for this carbon is also 4. Even after undergoing bond breaking, after forming the bond with two hydrogens individually, they are going to again get 4 valency. Yes, we should not forget one point here. All these tries, all these attempts carbon is trying to make in order to maintain its valency, or in order to get more stability, right? Yes, keeping that point in mind, here there is actually one pi bond is there. In place of that one pi bond we are going to get two new sigma bonds. Yes, there is one pi bond disappeared, and then two new sigma bonds have been formed. Similarly, if you try to understand, let me take, actually this is called, as we know very well, these are actually, this type of class of compounds are alkenes, and then finally after hydrogenation we are going to get something called as alkanes. Similarly, let me just take here, that is alkyne ko le lete. Yes, let us take alkyne, where we are going to have two pi bonds here. Okay, and now as I told you, in place of one pi bond, when we are getting two sigma bonds, in place of two pi bonds, obviously we are going to get 4 new sigma bonds, right? Yes, and now what happens in this particular reaction is, of course we need to take 2 moles of hydrogen here, because in order to form 4 new sigma bonds we need to take 2 moles of hydrogen. Yes, the normal existing bonds, carbon-carbon single bonds will be existed as it is, but in place of 2 pi bonds we are going to get 4 new sigma bonds, right? Hope you understood. It is clear, I guess, right? Yes, and now please do understand, this is actually, we call it as alkynes. And then after forming new sigma bonds, we are going to get alkanes. So not only in this particular scenario, wherever, maybe in the coming any of our upcoming lectures. So what I am going to tell you is, please, so you try to understand what is going to happen in that process, so that you will get to know some or the other hint to understand the reaction. Okay, agar addition ho raha hai, then what we observe, there will be a pi bond breaking, and then in place of that pi bond we are going to see new sigma bonds, right? Right. So here also in this particular Sabatier-Sunderens reaction, we are going to see the same. That is, in place of one pi bond, you are going to get 2 new sigma bonds with 2 hydrogens. Actually, we are taking hydrogen, so that is going to happen. And in place of alkynes, we are going to get 4 new sigma bonds, right? Yes, let us just go back. So that is what we need to do. Agar hum addition kar raha hai, then what we need to do, add that molecule onto the double bonded carbons, or add that compound into the triple bonded carbons. Don't disturb the remaining what do you say, that sp3 hybridized carbons ko disturb nahi karna hai. We need to focus on, if it is an alkene, then we need to add such a compound onto the multiple bonded carbon, that is sp2 hybridized carbon. And then on to triple bond, we need to add onto the sp hybridized carbon, right? Yes. Okay, so just let us continue. That is, hydrogenation is addition of H2 onto the double or triple bonded carbons. Yes. Okay, so what we need to do is, दोनों हाइड्रोजन्स में से एक हाइड्रोजन एक डबल बॉन्डेड कार्बन पे लगाओ और एक हाइड्रोजन को अनदर डबल बॉन्डेड कार्बन पे लगाओ, so that we are going to get a alkane as the major product, right? And then same onto the triple bond also. And the next that is hydrogenation of unsaturated hydrocarbons. Yes, this is what the Sabatier-Sunderens reaction is. Addition of, that is hydrogenation of unsaturated hydrocarbons, especially we know that they includes alkenes and alkynes, okay? And then in the presence of nickel or palladium or platinum. Yes, in this Sabatier-Sunderens reaction, we are going to take either nickel or palladium or platinum as the catalyst. These are going to play a crucial role. So that is, catalyst is a chemical substance which increases or which fastens the rate of reaction without undergoing any chemical change, or just by lowering its activation energy, uska activation energy ko compress karke, decrease karke, that particular catalyst is going to take the reaction in a faster way. Okay, right. And then yeah, catalyst as at particular temperature, that is 200 to 300 degrees centigrade, gives alkane as the major product, right? Yes, and then this reaction is called as Sabatier-Sunderens reaction. Let us just try to understand this reaction in detail. If you have this alkene, yes, this is an alkene. So इस alkene को हमने hydrogenation करा है, so nickel catalyst, and then this particular temperature, what we observe, yes, there is one pi bond, as I told you in the previous one. Yes, as we know, one pi bond is there in the generally in a double bond, so that particular pi bond will undergo bond breaking, and then we are going to see two new sigma bonds. Yes, I have shown it here, okay? And then see, this is called as ethene. Ethene को लिया, hydrogenate किया, and then we are going to get ethane. Yes, ethene gives ethane upon hydrogenation. Similarly, this other name also, that is ethylene. Okay, ethene and ethylene are both same. And then similarly, this is propene. Propene and propylene, both of them are same again. So ethene को hydrogenation करने से ethane मिला, propene को hydrogenation करने से propane मिलेगा, right? Simple, right? So similarly, if you take an alkyne, so 2 moles of hydrogen we need to take, obviously we know that, right? अगर हम एक ही मोल हाइड्रोजन लिया, then the reaction won't complete, or the reaction will not go to the alkane. The reaction will stuck in between the alkene itself. So the same reaction we are going to get in the alkene preparation as well. If you take controlled hydrogenation or only limited amount of hydrogen, then alkyne is going to give us alkene as the major product. So obviously the number of moles of hydrogen we are going to take in this reaction is also very important. अगर 2 moles of hydrogen लिया alkyne के साथ, then obviously it will go to the alkane. अगर alkyne के साथ 1 mole of hydrogen लिया, then the reaction will stuck in the, or reaction will stop at the alkene, right? Yes. And then that will see in the partial hydrogenation or controlled hydrogenation. Yeah, let's take few examples. That is, I have taken here ethine. So ethine upon 2 moles of hydrogen, it gives us ethane. Okay, and then similarly we have propine. Okay, propine को hydrogenation करने से propane मिलेगा. Yes, it is so simple. So these are a normal level questions, don't worry. And then I am going to take so many critical examples also. Just wait for that. And now next is methane. Yes, my question is, can we prepare methane by using this Sabatier-Sunderens reaction? Obviously no, right? Because Sabatier-Sunderens reaction runs with the alkene and alkyne, and then we need to do hydrogenation. Obviously, when it comes to alkene and alkyne, obviously the minimum carbons required to have an alkene or alkyne will be 2. And now with those 2 carbons of alkenes and alkynes, that is ethene and ethine, we are going to get ethane by doing this Sabatier-Sunderens reaction. But here, if we look at methane, methane has only 1 carbon. Obviously, we cannot prepare methane by using this Sabatier-Sunderens reaction. Hope you understood? Right. So obviously, there are several times we had a question that which of the following compound cannot be prepared by using Sabatier-Sunderens reaction. So that must be, methane. Methane must be the answer, okay? So methane cannot be prepared by using this method. Very important. Very important. And now, next point we need to look at, that is, only do we need to take nickel, palladium, platinum here to run this reaction? In addition to this 3 catalysts, we can also take PtO2, which is Adams catalyst, we call it as. So the same Adams catalyst also will do the same kind of work what nickel, palladium and platinum are doing. So that is what I mean to say is, that is PtO2 is also used in the hydrogenation. Yes, if you see, we can use nickel, palladium, platinum, and also platinum dioxide, that is Adams catalyst, for this hydrogenation. Very important. Okay, hope you understood. Yeah, I have taken a question here, that is, which metal is expected to take more temperature for hydrogenation of alkenes? Yes, we have seen nickel, palladium, platinum are generally used as catalyst in this Sabatier-Sunderens reaction. So now the question is, among these three metals, which takes more temperature in order to make this reaction happen? Yes, and for this we need to take the help of the periodic table, especially when it comes to nickel, palladium, platinum, they are present in 8th B group. So here we need to understand this particular question based upon their sizes. So generally when it comes to a group, within a group we know that atomic size increases from top to bottom. So nickel thoda chota rahega, and then palladium, and then platinum, right? Yes, and now keeping that point in mind, they have given nickel ko temperature T1, and then palladium ko T2, platinum ko T3. Yes, these are the three things they have given in the question actually. Okay, and now we need to define actually whether it is T1 greater than T2 greater than T3, which means that nickel takes more temperature or palladium takes more temperature, and then platinum, or vice versa. Okay, right. And now let us understand, since nickel is smaller in size, obviously the nuclear forces of attractions will be more compared to palladium and then platinum. So in order to overcome those nuclear attractions, so what I mean to say is, since nuclear attraction, so abhi dekho ye nickel ka nucleus hai, and then obviously there is a very less distance between nucleus and the outermost electron, so they will be in more interaction, and in order to activate such a smaller atom to undergo the reaction or to take the reaction carry forward, then obviously we need to give more temperature. And then when it comes to nickel se palladium mein aane ke baad, so what we see is size increases, obviously distance also increases, forces decreases, so obviously comparably less effort we need to put to activate this palladium compared to nickel. So similarly we have platinum also, and then in platinum the size will be much more larger compared to palladium. Obviously this takes a very less temperature to get activate to run this reaction. So that is what we need to understand. So I hope you understood. Agar samjho idhar T1 hai, either T2 hai, and then either T3 hai, obviously what is the order of the temperature? So obviously it is going to be T1 greater than T2 greater than T3. So hope you understood. That is what I have given here. So that is, because of smaller size of nickel, it requires more temperature to activate to carry out the hydrogenation. Hope you understood, right? That's what I have discussed. And now when it comes to the particular temperature, the same ethene to ethane, I have taken ethene to ethane conversion, and now in the presence of nickel it is going to take 200 degrees Celsius, and then with palladium obviously the temperature need to be decreased. Yes, that is what 150, and then when it comes to platinum there will be much decrease in the temperature, that is 27 degrees centigrade. Okay, yeah, hope you understood. This is an important type of question in this particular hydrogenation. Yeah, let's continue. That is next we have an important point need to be discussed here, that is, generally hydrogenation of alkenes stereochemically undergoes syn addition. Yes, this word is very important. And now what do you mean by syn addition? So during this hydrogenation, addition of two hydrogens will be takes place onto the same side of the double bonded carbons. So that is what is called as syn addition. Iska opposite hai anti addition. So two hydrogens or maybe two halogens, that will be that we are going to see in the halogenation of alkenes. Okay, yes, as far as this hydrogenation is concerned, we are going to see syn addition, that is addition of H2 takes place on the same side of the double bonded carbon. Yes, hope you understood. This point to be remembered, very important. This is a direct question asked in recent advanced exam. So just let us keep that point in mind. And now next, this is also very important. So when we are talking about alkenes, we will have generally cis and trans alkenes. So where cis alkene is said to be if two similar groups are present on the same side of the double bonded carbon like this, it is said to be cis, And then if if two similar groups are present on the opposite side, is said to be trans. Okay, and now particularly if we are trying to do hydrogenation or deuteration, so if you take hydrogen, then it is called as hydrogenation. In place of H2, if you take D2, then it is called as deuteration. Then we are going to see syn addition. For cis alkenes generally undergo syn addition, and the resultant compound is going to be our meso compound, which is going to show plane of symmetry. Yes, generally meso compounds are optically inactive due to internal compensation. And then we are going to have plane of symmetry for this meso compound. Chalo, let us take an example, that is cis alkene, and then cis alkene ko humne deuteration karne se those two deuterium atoms will be added onto the same side of the double bonded carbon, giving us two equal halves in this particular compound, which has a plane of symmetry. The rotations made by the upper half will be compensated by the rotations made by the bottom half, which is going to be called as meso compound. Hope you understood? Yes. So what we need to understand here is, if you take a cis alkene, then generally we see syn addition, and then the resultant compound is going to be a meso compound. Hope you understood? Chalo. And now let us comment about the trans alkene. Yes, if you see, these two similar groups are present on the opposite side of the double bonded carbon. So we are going to see syn addition only. Syn addition. But here we are going to get racemic mixture as the major product. So we are going to get two compounds which are enantiomers, which are non-superimposable mirror images as a major product. The trans alkene, upon reacting with deuterium molecule, we are going to get the two sets of enantiomeric compounds. So finally what we need to understand from this particular example is, trans alkenes generally undergo syn addition, and then we are going to get racemic mixture, whereas the cis alkene undergoes syn addition to give meso compounds. Yeah, let's continue. I have taken several examples upon this hydrogenation. So if you take ethene and then deuteration, then we are going to get two deuteriums need to be added onto the same side of the double bonded carbon, showing that it undergoes syn addition. And now when it comes to the next one, that is 3-methyl-but-1-ene. Actually, upon hydrogenation, it is going to give us, so what we need to do, just we need to add hydrogens onto the double bonded carbons. So it is going to give us 2-methyl-butane. Similarly, 2-methyl-but-2-ene, upon hydrogenation, again it is going to give, these two compounds are same, even though the alkenes we are taking are different, just we need to add hydrogens, that's it. Okay, and then next 2-methyl-but 1-ene, upon hydrogenation, again it gives us the same compound. Just one thing we need to understand, double bonded carbons need to be added with hydrogens, that's it. And then cyclopentene, I have taken hydrogenation, cyclopentane, and then deuteration, yes, we are going to get cyclopentane, and then cyclohexene upon hydrogenation, cyclohexane, and then the same cyclohexene upon deuteration, we are going to get deuterocyclohexane. Hope you understood? Right, let's continue. And then yes, I have selected few questions here on this particular concept. Let us solve them. That is, how many alkenes will give N-butane on catalytic reduction with H2 platinum? Yes, so we need to find out how many such alkanes are there which gives us N-butane. Butane dene wala alkenes kitna possible hoga? Yes, we know that is but-1-ene is possible. But-1-ene ko hydrogenation karne se N-butane milega. When it comes to but-2-ene, we have two possibilities, that is cis-2-butene is possible, trans-2-butene is also possible. And then anyway, if you take a cis-2-butene or trans-2-butene, upon hydrogenation, we are going to get N-butane as the major product. So overall, the answer is going to be 3. So 3 alkenes, 3 such alkenes are possible, which gives us N-butane upon hydrogenation. Yeah, next let's take the other example, that is, yes, here we have exocyclic double bond containing cyclopentane ring. So when it reacts with 1 mole of, particularly they have mentioned 1 mole of H2. If we take 2 moles of H2, then these two double bonds are going to reduce to give us 1,2 dimethyl cyclopentane, right? So agar hum samjho 2 moles of H2 is taken, then the final product is going to be this, right? Yes. But here particularly mentioned 1 mole only, then what we need to understand? So then here some different type of reaction takes place. Both the double bonds are cis to each other. Yes, if you observe, these two double bonds looks like they are cis to each other. Then what happens is a small rearrangement takes place, and then we are going to get 1,2 dimethyl cyclopentene. That will be the major product. No, not this is the major product. So since we are taking only 1 mole of hydrogen, we may guess that, you know, among those two double bonds, any one of the double bond may get also reduced into alkane group, right? But here, since it is cis to each other, then this is also not possible. The only possible product is, yes, this is what a type of rearrangement takes place in this. And now next we have another example, that is, yeah, if you look at this particular two double bonds are trans to each other, right? Yeah, they looks like trans to each other. Generally, this particular double bond is called as exocyclic double bond. So when we compare a trans double bond with an exocyclic double bond, generally exocyclic double bond will readily reduce compared to trans. And in this type of cases, we are not going to get any type of rearrangement, or no transition state will be formed like this. So directly we can say generally exocyclic double bonds will be readily reduced over the trans double bond. Okay, so hope you understood. That's why, you know, we are going to get this particular as the major product. There is no rearrangement as we have seen in the previous case. So this is what we are going to see. This exocyclic double bond is going to reduce, and then we are going to get this is the major product. Hope you understood. Yeah, let's continue. So here there is a question that they have given methyl cyclohexene upon hydrogenation. Just what we need to do, attach hydrogens. Okay, एक hydrogen इधर attach करना, and then another hydrogen. So we are going to get methyl cyclohexane. Okay, yes, it's a simple one. And then next we have a question here, that is, which of the following alkene has zero dipole moment? Yes, we know very well. Generally, trans alkenes will be expected to have zero dipole moment only if the two sets of groups are same. So what I mean to say is, if you look at the first option, these two hydrogens are present on the same side of the double bonded carbons, hence it is said to be cis. Obviously, this particular compound is going to have some or the other dipole moment. So obviously, this is not our option. And then next, if you look at, yes, this is trans. This is trans. Hence, these two dipole moments will cancel with each other. In दोनों का dipole moments तो cancel होगा, but these two groups are not same. So obviously, there will be the net resultant dipole moment. So obviously, this is also not our answer. If you look at this one, yes, so these two hydrogens are cis to each other. These two methyls also cis to each other. So obviously not the answer. So this compound also will have some or the other dipole moment. If you look at the last one, that is, yes, these two hydrogens are trans to each other, where we are going to see the cancelling of dipole moments with respect to each other. And then here two methyls also, they are opposite to each other, hence their dipole moments also cancel with each other. So hence we are going to see there is a net dipole moment for this particular compound is going to be 0. So that is what the answer. So what we need to understand is two sets of compounds. So here देखो, दो hydrogens भी same है, दो methyls भी same है. अगर if you observe the second option में ये दो hydrogens तो same है, but here there is methyl and ethyl. Those groups are not same. Then their dipole moments are not going to cancel with each other. Hope you understood. Chalo, let's continue. And then next, yes, here alkenes can be hydrogenated by using two types of catalyst. Okay, so we can take two types of catalyst here, that is homogeneous catalyst and heterogeneous catalyst. So these two are possible. When it comes to homogeneous catalyst, Wilkinson catalyst is particularly considered as homogeneous hydrogenation. Yes, in detail we are going to see separate reaction. Wilkinson catalyst, I have taken it separately. Yes, this is what called as Wilkinson's catalyst. एंड देन हेटेरोजीनियस कैटालिसिस के लिए हमने निकल पैलाडियम प्लैटिनम को ले सकते हैं और प्लैटिनम डाइऑक्साइड दैट इज एडम्स कैटलिस्ट को भी ले सकता है. ओके, एंड देन नेक्स्ट Let us continue. Yes, here this is going to be very important when it comes to the stability. Yes, generally we define the stability of alkenes based upon the heat of hydrogenation. Yes, very important. Order of stability of alkenes depends upon heat of hydrogenation. And now, how to define heat of hydrogenation in terms of alkenes? So heat of hydrogenation is directly proportional to number of hydrogen atoms on both the sp2 hybridized carbons. Now what does it mean? So heat of hydrogenation will be more for the compound in which the double bonded carbon having more number of hydrogens. sp2 hybridized carbons are nothing but double bonded carbons only, right? The more the number of hydrogens on the double bonded carbons, more is the heat of hydrogenation. And now the relation between heat of hydrogenation and stability of alkenes is inversely proportional. Now what does it mean? More the heat of hydrogenation, lesser is the stability. So the compound which is going to have more number of hydrogens on the double bonded carbons is going to be least stable because it has more heat of hydrogenation. So let us take one example to understand it easily. And then now if you see the first option, you can see clearly the double bonded carbons are not having any directly attached hydrogens. इस R ग्रुप में हो सकता है पर डबल बॉन्डेड कार्बन को डायरेक्टली अटैच्ड हाइड्रोजन्स नहीं है. So zero hydrogens on the sp2 hybridized carbon. Next, if you look at the second option, we can see one hydrogen which is directly attached to double bonded carbon. So here 0 and then one hydrogen. And now next, if you look at the third one, you can see two hydrogens on the directly attached sp2 carbon. So next we have two. Yeah, in this option you can see two hydrogens which are directly attached to sp2 hybridized carbon, which are trans, particularly trans. And then if you look at the next one, in this particular compound also you have two hydrogens which are cis to each other. Again you have two hydrogens only. And then next you can see three hydrogens which are directly attached to double bonded carbons. And then in the last option you can see four hydrogens. Yes, and then I have labeled it in the tabular form. So that is in the first compound you have 0 hydrogens on the sp2 hybridized carbon, and then the second one 1, 2, 3 and then 4. Yes, and now you can clearly say that in which case you see more number of hydrogens on the directly sp2 hybridized carbon in the last one. So this is going to have more heat of hydrogenation, and then this is going to be least stable. I hope you understood. Chalo, I have given it here, that is the relations to get the answer for this particular question. That is, heat of hydrogenation is directly proportional to number of hydrogen atoms on the sp2 hybridized carbons. Okay, so keeping that point in mind, yes, we can clearly write down the order. That is, this G is going to have more heat of hydrogenation since it has more number of hydrogens on the sp2 hybridized carbon, and then followed by F, and then yes, it follows like this. So G, F, E, D. So normally how do we compare when it comes to cis and trans? Cis will have more heat of hydrogenation because of the more repulsions. Since the groups are present on the same side, they will experience more repulsions. So more heat of hydrogenation, and then followed by trans, and then followed by a normal one. Yes, so this is the heat of hydrogenation order. More the hydrogens on the sp2 hybridized carbons, more is the heat of hydrogenation. And more is the heat of hydrogenation, more the reactivity, lesser the stability. Yes, yeah, if you observe, the G is going to have more heat of hydrogenation. The same order follows for the reactivity also towards the hydrogenation or addition of hydrogen. And the next, when it comes to stability, yes, stability is going to be the opposite one to this. So since A has less heat of hydrogenation, it is going to be more stable. Yes, stability order will be opposite to heat of hydrogenation. And now again there is one more important point, that is heat of hydrogenation is directly proportional to heat of combustion. So the one with the more number of hydrogens on the sp2 hybridized carbon is going to have more heat of combustion. Yes, we have a few questions asked in recent exams regarding or related to this. Let me solve that particular question also. Hope you understood. Heat of hydrogenation and heat of combustion is also directly proportional. Keeping that point, this is the order we are going to get. So let me just go to this. There is a question on this. The heat of combustion, which is exothermic, yes, we know heat of combustion is energy releasing process, so it is exothermic. For the 4C6H12 isomers, not necessarily in order, okay, fine, they have given delta Hc values are given for the 4 isomers. The isomers also they have given here, that is, yes, for C6H12 they have given the 4 isomers, okay. Just let us not worry about the compounds because they have already given. But now the question is, which of these values is most likely the heat of combustion of the first isomer? The best suitable value for the isomer 1. Okay, and to find out this, what we need to do is, chalo, let us just try to separate out the information. So among the given 4 options, if you look at the carbon core directly attached carbons are generally considered as alpha carbon. So let me just take the example of this. Yeah, the first option, if you look at, they have given, this is the compound we have, where these are the 2 double bonded carbons and these are the directly attached carbons to those double bonded carbons, which are nothing but our alpha carbons. Not only in this case, in any case, directly attached carbons to the double bonded carbons are called as alpha carbons. Yeah, here we have a CH3 group and here also we have a CH3 group, and if I'm not wrong, this is actually a CH2. So which mean इस अल्फा कार्बन के ऊपर 3 अल्फा हाइड्रोजन, 3 अल्फा हाइड्रोजन, 2 अल्फा हाइड्रोजन, all together we are going to get 8 alpha hydrogens in the first compound. And then similarly, yes, please try to understand 12 alpha hydrogens in the second one, and then only 2 alpha carbons are there, 2 hydrogens, so 4 alpha hydrogens, which is actually trans again. And then here also we have 4 alpha hydrogens, but which is cis. And we have a relation here is stability is directly proportional to number of alpha hydrogens also. We can also define stability for alkenes directly proportional to number of alpha hydrogens. So you can see the number of alpha hydrogens are more in the case of B. So that is the order. So B में alpha hydrogens ज़्यादा है, B, A, and then when it comes to cis and trans, obviously as I told you, trans में groups will be opposite to each other, lesser repulsions, more stability. So C and D. And now stability and heat of combustion, generally they are inverse to each other. Yes, as I told you in my previous here in this slide, we can easily conclude that stability and heat of combustion, they are inverse to each other. And then keeping that point in mind, so we can go with stability is inversely proportional to heat of combustion. So now this is the order, this is quite opposite to stability. So where B is greater than, A is greater than, C is greater than D for the stability, it is going to be quite opposite in the case of delta Hc order, D greater than, C greater than, A greater than B. So that is the order. And now what we can understand, since A is in the third in the list of the delta Hc, among the given options we need to go with respect to the third least number. So among the given 4 options, so here which is the largest value we have, 955, and then 953, and then 950, and then 949. So among the given 4 values, so the third one, that is A, the value which is suitable for the compound A is going to be 950.6. Hope you understood. This is so easy to understand. This question is asked in recent advanced 2022 paper. Yeah, next let's move into our next reaction, that is Wilkinson's catalyst. First of all, what is Wilkinson's catalyst? Wilkinson's catalyst is chlorido tris triphenyl phosphine rhodium 1. The oxidation number of rhodium in this particular Wilkinson's catalyst is 1. Actually, this is also important in the inorganic part, inorganic chemistry, particularly coordination chemistry mein aayega. And now the rhodium oxidation number is going to be +1. Okay, if you look at the IUPAC name, yes, this is what, chlorido tris triphenyl phosphine rhodium 1. So this is actually rhodium 1. And then yes, since the coordination number is 4 for rhodium, we can expect 2 different types of geometries. If the rhodium is undergoing sp3 hybridization, then it is said to be tetrahedral geometry. If it is undergoing dsp2 hybridization, then it is said to be square planar geometry. Particularly in this Wilkinson's catalyst, the rhodium is going to undergo dsp2 hybridization. So which is going to give us a square planar geometry. And then actually the color of the compound is reddish brown in color, and then DsP2 hybridization, square planar geometry. Actually for this reaction, for this particular reagent, the scientist Wilkinson is awarded Nobel Prize in the year of 1973. So what is that huge importance for this particular catalyst? Let's see. So actually this particular catalyst has a huge importance in the inorganic chemistry, but even in this organic chemistry also, this Wilkinson's catalyst is used in the homogeneous hydrogenation. And this particular reagent is awarded Nobel Prize in 1973. So Wilkinson's catalyst is used for homogeneous hydrogenation of alkenes. Okay, so let me just go with some examples here. So if normally, yes, you can see what is this compound called as. This is actually vinyl benzene. This is called as vinyl benzene. Yes, vinyl benzene. And the common name of vinyl benzene is a very well known compound, styrene. So styrene co-hydrogenation in the presence of Wilkinson catalyst. Just same thing we need to do. Add hydrogens onto the double bonded carbon. So we are going to get ethyl benzene. So we are going to get ethyl benzene. Yes, similarly, let us move with this. Yes, here we need to understand two things. That is, here you can see this double bond is out of this ring, and then this particular double bond is within the ring. And now generally a double bond which is present inside the ring is more sterically hindered compared to a double bond which is outside the ring. So if you see, yes, firstly, what do you mean by more sterically hindered? If you look at this particular double bond which is present inside the ring, this is almost responsible for these many carbons. Okay, so it is surrounded by so many different number of carbons, so which is nothing but more sterically hindered. So more number of carbons are surrounded to this double bonded carbons, whereas if you see this particular double bonded carbon which is away from the ring, so it is just having a, it is not that sterically hindered since it is surrounded by lesser number of carbons. So when we are trying to hydrogenate this type of compound which has both sterically hindered double bond within the ring and less sterically hindered double bond which is outside the ring. So generally this particular Wilkinson's catalyst is used particularly to hydrogenate the double bond which is less sterically hindered. Hope you understood what could be the product here. So this more sterically hindered double bond will remain as it is, whereas the less sterically hindered, that is outside the ring double bond, will be reduced by this hydrogen. So now this is again a different type of example, that is double bond which is present inside the ring and then a double bond which is connected or which is common to the ring, cyclic ring. And now such type of double bonds are called as exocyclic double bond. And now this particular double bond is with more sterically hindered, and then this is less sterically hindered comparably. Obviously by using Wilkinson's catalyst we are going to see the less sterically hindered, which is nothing but the exocyclic double bond is going to get reduced by using this Wilkinson catalyst. Okay. Right. Similarly, when we have a cis double bond and trans double bond, particularly this Wilkinson's catalyst is used to reduce cis double bond, not the trans double bond. Okay. Right. So you can see here, so this is actually the trans double bond, this is the cis double bond. So you can observe the cis double bond can be easily reduced by using this particular reaction. And then next we have these two double bonds are in conjugation, whereas this particular, the terminal double bond is not in conjugation because we have got a break here. So double, single, double, single, single, double. So this particular double bond has got a break, that is in terms of conjugation. So this double bond is generally considered as isolated double bond. So generally double bonds which are in conjugation will not be able to reduce that easily by using this Wilkinson's reagent. So we are going to get this isolated double bond. The double bond which is not in conjugation is going to reduce easily compared to the other double bonds. Hope you understood. Yes, these are all the applications of the Wilkinson's catalyst. Yes, and then next let's move on to our next reaction, that is coal-base electrolysis. So first of all, what we need to understand to study about the coal-base electrolysis. So we are going to take sodium or potassium salt of carboxylic acid, and then we are going to do electrolysis Yes, I hope you know a few things about the electrolysis. So just let me tell you, in the electrolytic process we are going to have electrolytic cell. ये जो है outer part, that is electrolytic cell. And now in the electrolytic cell we are going to take electrolyte. Yes, we are going to take electrolyte. Let us not worry what is that electrolyte. Okay, yes, and then after taking electrolyte we are going to take the two electrodes are going to be inserted in this particular electrolytic cell, and now one of the electrode is going to behave as anode and the other one is going to behave as cathode. Okay, yes, and now these two electrodes are going to connected with what do you say, that two different terminals of a battery. And now the electrode which is connected to the positive terminal of a battery is said to be anode, and the electrode which is connected to the negative terminal of a battery is called as cathode. So now we can say anode is a positively charged electrode, cathode is a negatively charged electrode. Once after taking the electrolyte, generally we are going to take the electrolytes as ionic salts. Ionic salts le lete, and then they will be able to give us different ions, right? And now once after we start passing the current across this battery, then obviously the current electricity passed into this particular electrolytic system, electrolytic cell, and then what happens is ions present in the electrolyte are going to shift towards the oppositely charged electrode. Yes, so what I mean to say is here हमारे पास A plus ions है, B minus ions है, and now as I told you, since this A, that is anode, is connected to the positive terminal of a battery, it is positively charged, and then cathode, which is connected to the negative terminal of a battery, it is negatively charged. Towards this negatively charged cathode, cations will tend to move. Towards this positively charged anode, the anions will tend to move. Yes, this is what happens in the electrolysis process. So that is, electrolysis is nothing but it is the thermal decomposition of an ionic compound into their corresponding ions in the presence of or under the influence of electricity. Yes, so once after passing this electric current, the ions will move towards the oppositely charged electrodes and then undergoes different process. Generally at anode we expect oxidation to take place, and then generally at cathode we expect reduction to take place. Yes, these cations will tend to move towards cathode and undergoes reduction. Anions will tend to move towards anode and then undergoes oxidation. Oxidation is loss of electrons, reduction is gain of electrons. We will see. So here in this coal-based reaction also we are going to do this particular electrolysis only. So here also we are going to take sodium or potassium salt of carboxylic acid, which is going to give us RCOO minus, which is a carboxylate ion, and Na plus, which is sodium ion. Right, and after when it reacts with water, we are going to get compounds at different electrodes. Our desired alkane, and with the carbon dioxide we are going to get it at an anode, and then sodium hydroxide or potassium hydroxide with hydrogen gas at particularly at cathode. Okay, so let us understand, let us not worry how it is being formed, so I'll explain you, don't worry. Okay, and then next if you observe, let us try to understand the reaction. The concentrated aqueous solution of sodium or potassium salt of carboxylic acid on electrolysis, alkanes containing even number of carbons along with CO2 will be deposited at anode, and NaOH or KOH, depending upon the salt we are taking, along with hydrogen will be deposited at cathode. Yes, this is what happens in this coal-based electrolysis. Hope you understood. Now let us understand the reaction in a easier way. That is, let me take here sodium salt of carboxylic acid. This is actually called as sodium salt of carboxylic acid. It is reacted with water. Let us take H2O. We need to take 2 moles actually, 2 moles of sodium salt of carboxylic acid. or potassium salt of carboxylic acid with 2 moles of water need to be taken compulsory. And now what happens is, finally we are going to get products based upon the mechanism, but it is very easy to predict or identify the final product just by looking at the sodium or potassium salt of carboxylic acid we are taking. Just try to understand. So what I am trying to tell you is, you just do one thing, ये जो R bond C bond जो है इन दोनों को break करो, and then you try to take or try to form a new bond in between them. And now similarly you try to break the bond in between oxygen and sodium, and then we are going to get 2 moles of carbon dioxide. And now similarly just try to break oxygen hydrogen bond and then try to form 2 moles of sodium hydroxide, and then finally we are going to get a hydrogen gas also. So it is simple to remember, I hope. The first 2 products we are going to get at anode, and then the second 2 products we are going to get at cathode. Okay, yes. And now let us see how this particular reaction is being taking place. Let us not worry about that. I have told you simple way to predict the products. Just suppose, let's say, what I mean to say is, suppose let's say they have given sodium salt of ethanoic acid. Suppose let's say, actually we know very well that this is ethanoic acid, this is ethanoic acid, and now when it comes to sodium salt of ethanoic acid, we need to take H place में Na ले लेना, right? So this is called as sodium salt of ethanoic acid. इसको coal base electrolysis करने से what could be the product, what could be the alkane we are going to get? As I told you, in this coal base electrolysis we need to take 2 moles of sodium or potassium salt of carboxylic acid, whatever we are going to take. And now when we do this coal base electrolysis, as I told you just now, we need to break bonds here and then attach this. Yes, this is the major product here. Mostly they are going to ask us about alkanes only, not about the byproducts. At the same time, byproducts are also important. It doesn't mean that I'm asking you to leave completely, but it is not like that. Okay, byproducts के ऊपर भी बहुत सारे बार questions पूछा है, so please try to understand. So my intention for asking this question is simply by taking sodium or potassium salt of carboxylic acid, that is particularly sodium or potassium salt of ethanoic acid, then we are going to get ethane as the major product. Yes, as I told you, just break this CC bond and then you try to form new bond will be formed between 2 different alkyl groups here. Okay, right. Similarly, anyway, this compounds will be common in all the reactions. So NaOH, NaOH and H2H2. Okay, right. So ethane will be formed. Hope you understood. And now let's go back. 2 moles RCOONA and then water, and then we are going to get RR and then CO2 and then NaOH and H2. Yes, one more important point, that is in the end of the reaction, in our resultant electrolytic cell, we are going to see NaOH, which is a strong base. So since it is a strong base, our resultant solution का nature भी strong alkaline medium में होगा. So it is a strong basic, it is going to be strong basic. Okay. So and now if it is a strong base, then obviously pH will be greater than 7. Obviously, right? So pH will be greater than 7. So there are questions possible from this part. So what is the nature of the final resultant solution in the coal base electrolysis? It is going to be basic. And what could be the pH value for that? Obviously more than 7. pH more than 7, pOH less than 7. Is it right or wrong? Yes. You try to understand that point. Yes. And now next if you take, yes, as I told you, particularly if you take sodium acetate, it is also called as sodium ethanoate also. Sodium ethanoate. इसी compound का नाम है sodium ethanoate or sodium salt of ethanoic acid. All the names are same. Sodium ethanoate or sodium salt of ethanoic acid also. So which is going to give us ethane as the major product. Yes. And now my question to you is, we couldn't be able to prepare methane by using Sabatier-Sunderens reaction. And now if I ask you, can we able to prepare methane by using this coal base electrolysis? Obviously no, because methane has only 1 carbon, but here we are going to get even number of carbons containing alkane. But methane has only 1 carbon, which is not even, and which is not the suitable process to prepare this particular methane. So we can conclude that coal-based electrolysis is not used to prepare methane also, like the Sabatier-Sunderens reaction. Let me give you some more examples of this type. So by the end of the reaction, the solutions become basic due to the formation of NaOH or KOH. Hence the pH increases. Yes, we can clearly understand that point from the reaction, right? Yes, and now this method is not convenient to prepare unsymmetrical alkanes, which is nothing but odd number of carbons containing alkanes ko prepare karne ke liye it is not that suitable. Okay, right. And then yes, let us now try to understand the mechanism. This mechanism is going to be very beautiful. In fact, agar mechanism samajh mein aaye to yes, we can understand everything. So let us try to understand its mechanism. It is going to be very important. So generally we are going to take sodium or potassium salt of carboxylic acid. Yes. And now 2 moles of such compound is going to be taken, and now generally it is going to break into its 2 ionic forms, that is RCOONA and then 2 moles of sodium ions, right? And now next if we move on to water, yes, we have 2 moles of water also. So we are going to get 2 moles of H plus ions and then 2 moles of OH minus ions. So generally this reaction happens within the electrolytic cell, since we are taking these compounds in the cell. Okay, right. And now particularly, as I told you, actually if you observe carefully, how many types of anions and cations are there here? So RCOO minus and OH minus, these are the anions we have, and then H plus and then Na plus, these are the cations we have. So generally in a particular electrolytic cell, we may have any number of or any types of anions and cations, but when we start passing the electric current through the circuit, all the anions will move towards the anode, all the cations will move towards the cathode, but among all of those anions and cations, only one particular ion is going to get deposit onto that particular electrode. This is what very important. Anyway, this particular concept is particularly there in the electrochemistry part, which I will be giving you in the electrochemistry video lectures. Okay. Yes, Faraday's laws of electrolysis बोल के subtopic है, very important. So there you will get to know. Okay, and coming back to our discussion, that is, out of all those different types of ions, cations and anions, the only one particular cation or anion is going to deposit at its particular electrode. And now how to define, among these RCOO minus and OH minus, how to say which particular anion is going to deposit. And then among these cations, which ion is going to deposit? That depends upon its deposition tendency. So deposition tendency के ऊपर depend होगा. And now generally RCOO minus and OH minus के दोनों में comparison में RCOO minus will have more deposition tendency, hence it undergoes oxidation at anode. Okay, and then when we compare H plus and Na plus, among these two, H plus has more deposition tendency, hence it deposits at cathode. Okay, so let me just try to write down the reactions involved at anode. Okay, anode के पास कौन सा reactions होगा एक बार देखेंगे. And now as I told you, yes, we are going to have R C double bond O. What is the meaning of minus actually? It means one extra electron. Generally oxygen belongs to 6th group, so it has a 6 valence electrons, but it has a negative charge because of one extra electron. Yes, so that is what we are going to consider here. And now at anode generally oxidation takes place. What is oxidation? Loss of electrons. ये जो extra electron है, it is going to go out. So what we are going to get here is, so R C double bond O, and then there is oxygen. Oxygen का खुद का electrons उसी के पास है. Yes, and now from each oxygen, actually we have taking 2 moles of such carboxylic acid salt, right? So we are going to have 2 electrons will be released. So इधर एक oxygen के ऊपर एक extra electron होगा. So 2 moles of such carboxylic acid salt है. So obviously we are going to have 2 electrons will be coming out. And now if you observe carefully, this is a free radical, this oxygen has a free electron. Yeah, in this particular R and carbon के बीच में जो भी bond है, this electron belongs to the R group, generally the carbon present in the R group, and then this is the carbon's electron. And now if you try to understand carefully, just let me try to write down this a bit clearly. Yes, and now you observe, yes, that is the extra electron I am writing here of the oxygen. अभी देखो ये कार्बन के पास उसका bond है, bonded electron है. This particular bond is going to undergo bond breaking here, and this carbon's electron is going to form a bond with this oxygen, giving us, so इधर हमको दो alkyl free radicals मिलेगा, and then this carbon electron will be going to form bond with the oxygen to give us CO2. Yes, this is what we are going to get. And now these two alkyl free radicals, again they combine with each other. Okay, so we have two such alkyl free radicals. These two are going to combine to give us there is a RR bond, which is a new alkane. We have got it. I hope you understood. Right, this is simple mechanism of coal-based electrolysis. This happens in all the coal-based electrolysis reaction. So especially when it comes to entrance exams, yes, even the mechanism part are also important, because questions we can get from this particular mechanism part also. But just to identify the product, this entire drama is not at all important. Just हमको क्या समझना है? Obviously, देखो coal based electrolysis में we are going to take 2 moles of sodium or potassium salt of carboxylic acid. इसको water से 2 moles of water से electrolysis करने से we are going to get a new RR bond. That's it. जो भी हमने सोडियम सॉल्ट ऑफ पोटेशियम सॉल्ट ऑफ कार्बोक्सिलिक एसिड ले रहा है, then we are just supposed to bond these two alkyl groups with each other in order to predict the final alkane product. Yeah, let us see the cathodic reactions also. What happens at cathode? Yes, at cathode generally we know that reduction takes place. Reduction is gaining of electrons. So firstly, हमारे cations क्या क्या बचा हुआ है, then there is H plus ion and then Na plus ion. As I told you, H plus ion wins over the Na plus ion, so hence it undergoes reduction. So here two H plus ions है, and now the two electrons which we have got in the anodic reaction, those two electrons will be grabbed by this H plus ions, and then we are going to get H2 at cathode particularly. And we have some other ions left in the solution. So left reactions, if you observe carefully, so what are the ions left in the particular solution? That is 2 Na plus and then 2 OH minus. They are going to combine with each other. We are going to get 2 moles of NaOH. This is what exactly happens in the mechanism. That is what, yes, I have given it here clearly. So please try to understand. Okay, yes. And now this is what we are going to take, and then 2 electrons are going to come out, and then again finally we are going to get methyl radicals, and then those methyl radicals are going to combine to give us ethane. And then yes, yeah, look at this particular cathodic reactions. Yes, as I have shown you just now, you can clearly understand. And then left out the reactions in the electrolytic cell will be sodium hydroxide. Yeah, and then next let us move. Yes, I have given several examples here. Just you try to predict the products here. I have taken sodium salt of propanoic acid. So what we need to do, just break the bond here and then attach a bond here. That's it, right? So at anode we are going to get butane as the major product. Hope you understood. In addition to butane, which is actually a major product, trace quantity of ethane and ethene are also formed. Yes, this is a very beautiful question asked in recent mains. That is, the same question is asked. Okay, in addition to butane, what are the compounds are formed in trace amounts in this particular coal-based electrolysis of sodium salt of propanoic acid? Then we need to go with ethane and ethene are also formed according to the mechanism only. Okay, right. And now let us just go back to this. We have a dicarboxylic acid. So just what we need to do, break the bond here and then keep a double bond. That's it. This is the major. And now, yes, we have one other product also possible. If we are going to take 2 such moles of sodium or potassium salt of carboxylic acid, we are going to get a ring in between this. How we are going to get such products here? Let us just try to understand the mechanism. Okay, yes, this is simply, we can say that is cyclohexene we are going to get just by taking the help of 1 mole. Just actually here we no need to take 2 moles of this particular sodium salt of carboxylic acid, because in order to form a new bond between carbons, already 2 carbons are available here. Just we need to break the bonds, just take the double bond, that's it. But in case वो भी possible है, yes, coal based electrolysis is nothing but taking 2 moles of such sodium or potassium salt of carboxylic acid. So here in this case, this particular bond is going to go out and then free radicals are going to form. So 2 such moles of free radicals are going to form, and then you are going to get, yes, these particular free radicals are going to combine to give us this product. Okay, so these 2 products are possible. Okay, let us move on to this. And now if you take sodium salt of succinic acid, yes, succinic acid sodium salt liye to already we have a bond, so just break here and then take us. So this is coal based electrolysis is used to prepare alkenes also. So this particular reaction again we are going to get in the case of alkenes preparation. Yes, we can also take this sodium salt of malic acid in order to prepare this ethine. Yes, this is called as malic acid, where both the COO-Na groups are attached to the double bonded carbons. Break the bond here and then take it another bond, so which is going to give us ethine is the major. So which mean that coal based electrolysis is also used to prepare alkynes as well. So this reaction is again going to appear in the preparations of alkynes. Okay, and then next let us go to this particular reaction, that is again I have taken a dicarboxylic acid salt, where we are not going to get a triple bond. Already double bond is there, so within the ring we can't have a triple bond because of the bare strain theory. So this is the ultimate product we are going to get. Yes, so as I have shown you just now in the previous case, in this case we have got 2 products. One is the normal product and another one is a tricyclic actually. Okay, yes, this particular possibility is not there. If in case if you expect that particular scenario here, then you get the triple bond. Yes, that is highly unstable. Okay, right. And now let us just go back to this. Yes, I have taken another example, which is a dicarboxylic acid salt again. So you just break the bond here and then take a free radical, just break the bond here, take a free radical, and then those 2 free radicals need to be attached. So these are the 2 carbons. Yeah, these are these 2 particular carbons. So these are the examples I have collected from so many previous papers. So you please try to make use of this. With this I am going to end up our video, which includes Sabatier-Sunderens reactions, Wilkinson's catalyst, and also coal based electrolysis. Hope this video will help you a lot in solving the previous JEE and NEET questions. So I request you to watch the video completely, and then I request you to follow my channel regularly to get the most of the benefits. Since you are in the IIT and NEET preparation, my channel will help you a lot. See, please, I request you to just forward my channel, suggest my channel, refer my channel to your friends and family members, those who are in the preparation of IIT and other competitive exams. Thank you so much for watching the video. Soon we are going to come up with the remaining reactions of, we have so many preparation methods of alkanes, not only these 3. So in the coming video, I am going to include decarboxylation and then a few other preparation methods of alkanes. So until that, thank you so much. See you soon.